Let us wrap up the MCMC chapter with a particular application on the Bayesian change point model. In this example, we are going to fit a very commonly used model in statistics, the Poisson change point model, under the Bayesian framework, and we will implement a Gibbs sampler for Bayesian parameter estimation. We will look at the data set on the number of coal mine explosions that resulted in 10 or more deaths each year from March 15, 1851 to March 22nd of 1962. This data set is available in the boot package and is called coal. The data set has one variable called the year. And in this variable, it contains the recording of the year actually has decimal places, perhaps indicating the months, that such incident with 10 or more fatalities occurred. If we tabulate the years, we'll be able to see how many explosions occurred in each year. And let's look at the time plot for this. Here's a time plot for the number of explosion incidents each year from 1851 to 1962. The x-axis is the year, and the y-axis is the count of such incidents. As you can see, it appears that at some point, just by eyeballing somewhere around here, the rate of disasters decreased, indicating that there might be a change point where before the change point and after the change point, the rate of disasters are different. This is where the change point model can be useful. Let yi be the number of disasters in year I, where 1851 is year 1. Let's assume that yi follows a Poisson distribution with parameter mu for all i's before k, and yi follows a Poisson distribution with a different mean lambda for all i's after k, so from k plus 1 to n. In other words, before the change point in a particular year and after the change point, the rate of disasters are different. The parameters to estimate under this model are k, the change point, and mu and lambda, the two Poisson parameters before and after the change. We will use a Bayesian model with independent priors. Here, let's set the prior of k's to be the discrete uniform distribution that's evenly distributed with equal probabilities on values 1, 2, all the way up to n, the last time point. And let mu to have prior distribution that's gamma with shape 0.5 and the rate be 1. And also similarly, let's set the prior of lambda to also be gamma with shape 0.5 and rate be 2. Here, B1 and B2 are additional parameters with priors that are also gamma. Particularly, we will use the gamma distribution with parameters 0 and 1. One thing you might notice is that gamma 0, 1 is not itself a valid density. Ordinarily, you will want the shape parameter, which is the first parameter here, to be greater than 0. However, even though it is not itself a proper density, it can still be quite commonly used in Bayesian inference. Such priors that are not proper distributions are known as improper priors in Bayesian analysis. To run the Gibbs sampler for parameter estimation, in other words, to draw samples from the posterior distribution of the parameters given the observed data, we must be able to specify all of the full conditional distributions and draw from them. This is the first time we might have mentioned the word full conditional distribution. This is essentially the conditional distribution of J given all of the other parameters. So it's just a simplified name for the conditional distribution of xj, the jth parameter, given everything else. So recall that we want to draw from the full conditional distribution of each parameter in Gibbs sampling. Here, for example, to draw a sample of k, we need to know the distribution of k given y mu lambda b1 and b2. So this is xj, and these guys are x minus j. Note that the conditional distribution in general of A given B is given by the joint density of AB divided by the marginal density of B. So here, taking K as an example, the conditional distribution of K given y mu lambda B1 and B2 is equal to the joint distribution of y mu lambda K B1 and B2 and divided by the marginal distribution of y mu lambda b1 and b2. No k here. The book does not go over how each fold conditional distribution was found, so if you want to find out, I have included handwritten notes on the derivation of the fold conditional distribution for each parameter. For now, let's skip the handwritten derivations and assume that we have done the derivations in this way and we have found out what is the fold conditional distribution of each of the model parameters. Let's first look at K's. Denote the sum of the yi's, the number of explosion incidents from year 1 to year k by sk. Similarly, let's use sk prime to denote the sum of the yi's after time k, so from k plus 1 to n. Notice that sk prime is equal to Sn, the sum of the total number of incidents minus Sk. And here, Sk is the count of accidents before the change point, and Sk prime is the count of the number of accidents after the change point. Then we can find out that the conditional probability that K, the change point, is equal to K given y mu lambda b1 and b2 is equal to L of y k mu lambda divided by the sum from k star equals 1 to n of L evaluated at y k star mu and lambda. Here, L of y given k mu lambda is the likelihood, and this is equal to the product of the Poisson densities with rate mu from time 1 to time k, so the pre-change ones. And then times the product of the Poisson probabilities post-change from time k plus 1 to n with Poisson mean lambda. After some combination of terms and simplification, we'll find out that the likelihood is equivalent to e to the power of k times lambda minus mu times mu divided by lambda to the sk power. And here are the full conditional distributions of mu lambda b1 and b2. Specifically, mu given the rest of the parameters and the observed data will follow a gamma distribution with shape 0.5 plus sk and rate k plus b1. Lambda is also going to have a conditional distribution that's gamma with shape 0.5 plus sk prime and rate and minus k plus b2. b1 and b2 will also have gamma conditional distributions with shape 0.5 and rates of mu plus 1 and lambda plus 1 respectively. In the Gibbs sampler, at each iteration, we will iteratively draw k, mu, lambda, b1, and b2, conditioning on the observed data y and the current values of the other parameters. There you go. Sorry, I don't know what I clicked on. So the first thing we want to do is to slightly rearrange the data so that our input y actually matches with our model formulation. Let's recall that in the raw data, we have the record of the year such incident occurred. So one thing we want to do first is to transform the data into counts between 1851 and 1962 of the number of incidents of explosions in each particular year. This can be done by tabulating the year data and then taking the entries from 1851 to the length of y, so 1962. The resulting y is going to be a vector with length 112. And each of the entries will record the number of explosions that occurred in that particular year. And this count will be discrete and will be greater than or equal to 0. Now let's set up the Gibbs sampler for the change point model. Our n, which is the largest value that the change point can take, or the total number of time points in this time series data, is the length of y. So n is equal to length of y, the length of the time series data. We will run a total of m equals 10,000 iterations for the MCMC, and we will create 0 vectors of mu, lambda, and k for storing the MCMC draws. You might notice here that we're not storing the B1 and B2s because they aren't the parameters of interest for our current change point model. We will then create a vector L, which is now a 0 vector of length n, for storing the likelihoods for each possible k value ranging from 1 to n. This will come in handy when we try to obtain the sample of k from the conditional distribution. Now let's set some initial values for each parameter. The initial value of k is set to be a random number between 1 to n. Initial value of mu, lambda, b1, and b2 are all set to be equal to 1. And here's the code for the Gibbs sampler. At each subsequent iteration, we want to iteratively update each of the model parameters. Let's start from updating mu. We know that conditioning on the observed data and the other parameters, mu will have a gamma distribution with rate given by 0.5 plus the sum of the y's from time 1 to time kt. Kt is the last k draw. And the rate is given by kt plus b1. So after computing the r, the shape, we'll be able to draw a random sample from the gamma distribution with shape equals r and the rate kt plus b1. Next, let's draw lambda in a similar manner. First, we will calculate what is the shape parameter for lambda. Given the other parameters' current values and the observed data, we know that the shape for the lambda gamma distribution will be equal to 0.5 plus the sum of all of the y's if kt plus 1 is larger than the total number of time points. So in other words, if there's no change point, so if the change point is the last point, it means that there's no change. Then we'll set r equal to 0.5 plus the sum of y's. Otherwise, the shape parameter for the conditional distribution of lambda will be 0.5 plus the sum of y from kt plus 1 to n. And then we'll generate lambda from the randomly from the gamma distribution with shape r and rate n minus kt plus b2. Subsequently, we can update b1 and b2. They are respectively randomly generated from the gamma distribution with shape 0.5 and rates given by the current mu plus 1 and the current lambda plus 1 respectively. After updating b1 and b2, we will generate the next k, conditioning on the other parameters and the observed data. To generate k, we need to first calculate that ratio. So the likelihood plugging in k divided by the likelihood plugging in k stars sum up from 1 to n. So the jth entry in the L vector for storing the likelihoods from 1 through k is equal to the exponent of lambda minus mu times j times the ratio of current mu divided by current lambda to the power of the sum of y's from the first entry to the jth entry. And then we know that the probability, conditioning on all the other variables and the observed data, the probability that k takes any particular value is given by this L vector divided by the sum of the L vector. So we will sample the next k to from 1 through n, where the corresponding probabilities for each of these time points between 1 and n is given by L divided by sum of L. So you can see in each iteration, we update each of these parameters iteratively. And when we update each parameter, we condition on the most recent draw of the other parameters. You can see over here, we plug in mu I and lambda I, etc. So after running this MCMC cycle for a total of 10,000 iterations, we can look at the chain plots of the last 1,000 draws for each parameter. So in other words, we'll look at the draws from time point 9,001 to 10,000 in the MCMC chains. The way we generate the chain plots is the same as before, where the x-axis is the time or the iteration index ranging from 9,001 to 10,000. And the y-axis is the corresponding draw for that parameter in that iteration. And here are the results we got. So the three plots are the plots for the chain of k, which is the change point, lambda, the pre-change Poisson mean, and mu, the post-change Poisson means. And you can see that it appears all of them have stabilized. Let's try to take a look at the posterior densities of each of the parameters. So here we will toss away the first 5,000 iterations as burn-in cycles, but the 5,000 is actually a quite arbitrary choice over here. We'll do histograms of the samples we got, excluding the initial 5,000 iterations, and then frequency equals false, indicating we want to take a look at the densities. And here are the posterior densities of the three parameters. You can see that the posterior mode of k is somewhere around 40. The posterior lambda has a mode that is somewhere close to slightly less than 1. And then for mu, you can see that the posterior density is centered around somewhere around 3, I think. So you can see the change point actually occurred, probably is estimated to be around the 40th year. And then before that, number of accidents follows a Poisson distribution with a follows a Poisson distribution with mean that's less than 1. I think I'm flipping it. So this is the pre-change. So this plot below for the muse is the pre-change one. So you can see that before the change point, it seems like the Poisson distribution has a high rate, that's above 3. And then after the change point, the rate is much lower, which is less than 1. So let's also take a look at the post-burn-in posterior point estimates of the parameters. We can take the mean of the case, tossing away the first 5,000 iterations, and that's somewhere around 40. Indicating that starting at the change point estimated using the Bayesian framework is around 40. From year 40, the rate of explosions has changed. The posterior mean estimate for mu, which is the pre-change Poisson rate, is 3.12. And then post-change, the Poisson distribution mean estimate is 0.92.